happy because they're interesting and they're beautiful structure. So we'll get there in a minute. I did want to make a brief administrative announcement. I was talking to some of the demonstrators yesterday, and they said that attendance is dropping at the workshops. Everybody's busy, I understand, but I encourage you to squeeze out those 2 hours in your week. There's a lot of good problems that really reinforce things. If you're going and you're sitting there feeling smug about the fact that you're showing up, see if you can peer pressure your friends to come too. It's just, it's an opportunity not to be missed, and there's a lot of good stuff there. Another thing that I sort of want to highlight that's kind of happening in the class is almost up until now, it's been this matter of convenience that you have this one class, 1115, 1116, which does this analysis on one side and this algebra on the other side. But you can be forgiven for almost thinking of them as two classes, except for they have one model site, because the material sort of looks very separate. And one thing you should notice now that's going to continue for until the end of the term is that that's really changing. Now we're really seeing that these subjects are inextricably linked to each other. So just as an example, so we've highlighted this. What you're talking about in the analysis part is differentiability, right? So you're asking, when can you approximate a function by a linear function, right? So this is saying, how can we take things that don't live in the linear algebra world and meaningfully use tools of linear algebra to study them, okay? And here we are over in algebra land, but we're taking our vector spaces and all of a sudden we have norms on them, we have distances. There's proofs of things that turn out to be easiest to do by showing some set of operators is dense and some set of other operators. Some of this stuff was kind of lurking in the background, some of it will come up explicitly in the next couple of weeks, but it's a nice time to kind of step back and realize that even though these subjects sort of chug along separately for a lot of the semester, there really are connections, and you now have enough structure built up that you can start to see them. So if you notice some of these things and you have questions about them, don't hesitate to ask me or Griff about them, because it's one of the nice ways to look at mathematical subjects. These aren't, they don't come to you in little boxes where like, this is the analysis box, this is the algebra box. It's all mathematics, and we just have to divide it up for convenience. So, okay, so that's my sales pitch. But let's talk about adjoints. So I gave you the definition of the adjoint of an operator last time, which is a slightly narrower definition. Let's give the proper definition of an adjoint here on the board. So we're going to start with V and W, or finite dimensional inner product. What is this? And let's suppose that we have a linear map from V to W, okay? Our definition of the adjoint is that it's a map that satisfies a certain property. So we'll say it like this, we'll say T star from W to V is the adjoint of T if we have a certain property hold. So the relationship is that if you take the inner product of TV, sorry, let's make this, that's a V, my V's pointy, TV with W, for all V and V and all W and W, this is the same as taking the inner product of V and T star of W. For all V and V, W and W. Okay? And so let's just notice something is that one thing is we have two different inner product spaces. So each of the expressions on either side of this equal sign is just a number, but notice that they come from evaluating different inner products. So this is T of V lives in W, so this is the inner product on the space W. And T star of W lives in V, so this, assuming this T star exists, so this is the inner product that's defined on V. Okay? So if we wanted to be really pedantic about this, we could use different notations, but the reason I'm just putting an inner product here is only one of these makes sense. But you could imagine a problem where one of these is an inner product that's a dot product in Euclidean space, and another one is a some sort of integral expression. So just be aware that the actual process for computing these inner products could be very different. Okay? So the question I left you with at the end of class last time is, why should we expect such a function actually exists? Okay? And I encourage you to take a look at the section in Axler, because it's a big section, it does a lot of stuff. So what I want to try to do today is give you some of the highlights and some structure for that. We're not possibly going to cover everything in that section in class, or else I'd just be sort of copying the book onto the board, which is probably better to do. But let's start with what he has really on the first page, which is, why should we expect such a thing actually exists? Okay? And one of the tools that's going to come up again, that was mentioned peripherally last time, that's really central today, is the Riesz representation theorem. So it's going to give us a way to say, we can find, if we have a function, we can find something that, so that taking the inner product against a particular vector gives us the same output. So let's go ahead and see this. So, so let's start by just fix some w and w, okay? And we want to try to figure out what in the world t star of w should be. So here's our question. And so if we want to do this, let's go ahead and just try to evaluate. So I want to define a linear functional. So let phi be a function, be a functional, which is just going to be, let's write it this way, phi of dot is just take the inner product with dot, okay? And so, oh, sorry, that's not the one I want. I thought we were going to get there. I want something different. I want something much more interesting. I want the functional on v, so I want phi of v. So how am I going to get a number out of this? So phi should be a linear functional, and I'm going to define it by first apply t to v, and then take the inner product of w. So, much more interesting. Okay. So this is going to be a linear functional. But since it's a linear functional, then that says that there has to be something that anytime we have this little functional, we can accomplish the same thing by just taking the inner product of v with that thing. So by the Riesz representation theorem, there exists something I'm going to call it. I'll just call it x. We'll figure out what there exists an x such that phi of v is equal to the inner product with x. So let's notice, where does x live? Well, this is taking an inner product of v and something else. So this is an inner product in v now, okay? And so that means that x is a vector in v. And then we found what our t star of w is. So find t star of w to be equal to x. Okay, so we've just shown such a thing exists. Now, we haven't said that much about it as a function, but we've just said if you give me a w, I know how to tell you what t star of w is. And that's a way to define a function because we just defined it pointwise. We would like to have a more interesting function. So one of the things you could ask is, what's the structure of this function? And as we could have, first question is we could say, well, all the functions we like are actually linear functions, and in fact, this is also a linear function. So this is not that hard a thing to check, but it says we're on the right track, that this is something interesting to study. We don't really like nonlinear functions. Okay? So fine. So we have some linear function. We're not going to put that in our definition, but it's one of the basic things we want to know about the adjoint, is that if you have a linear map, its adjoint is also a linear map. There's another function lurking behind here, which is the function that takes linear maps from v to w to linear maps from w to v. And now the next question we could ask is that a linear map? Okay, so here's a question for you. Question. Define big phi that goes from the space of linear maps from v to w to the space of linear maps from w to v by big phi of t equals t star. So if we believe this projection, this proposition is fine. And here's my question: is big phi linear? Okay. So this is a question for you. I'm going to give you guys 2 minutes to try it. I'm going to circulate. Feel free to take any questions on this. But there's two things we have to figure out: is how, what linear structure are we looking, and do the axioms we'd have to check hold. So see what you can do. Feel free to talk to your neighbors. I'm happy to come around and chat, and we'll reconvene in 2 minutes. And I want to know if it's linear, or if it's not linear, why not? See what you can do. What do you guys think? How do you even start?
Look at the definition. Look at the relationship between t and t star.
Sorry, say it again.
Look at the relationship between these two.
And well, that's right. So this is the input of the function, this is the
Yeah,
output, right?
yeah.
So if we want to check linearity, what are the two things we're verifying?
The multiplication and additive.
Okay, and what objects are we at? So like the additivity one, what are we adding? We're saying.
We're saying that if we add some two V's together and two W's.
Not to no. So let's look. We're looking at so this is somehow why where are our objects living? This is a function from a space of linear maps to another space of linear maps. But forget about that they're space of linear maps. It's just from one vector space to another. So we want to check if you add two vectors in the first vector space.
Yeah.
And what's our first vector space? Is the space of linear maps from V to W. So our linearity is saying what happens if you have two linear maps like S and T, if you add them together and take their adjoint, versus if you take their adjoints and then add them together.
Yeah.
Right?
Mm-hmm.
So somehow the point is, you said exactly the right thing for why this is questions we're thinking. We're not adding two little v's together, we're adding two functions together. Does that make sense? Okay, so see if you can.
So this is really about if you add two tables together,
You get
almost
like this.
well, if TNS, yeah, that's true. Let's distribute TNS.
Okay, great. What do you think?
So if you got
Okay, so since we're not going to specify these happen to be the complex numbers, is it unknown or is it unknown?
It's just like,
Okay, great. So, yeah, great.
I guess.
and then you can add two T's. So like this. Actually add two T's. Anyway, and then the adjoint.
See if you guys all have the questions right, then we can Can you do that?
Yeah.
Like if we have this. I think if
You can, you stop playing.
I'm not sure about multiplication.
Yeah, that's what I was thinking. I feel like there should be a function. That should be a lambda function.
Okay, so let's just reconvene for a minute. Most people were setting things up correctly, and that's great. So if we want to show this is a linear map, it's the usual setup, right? We have to check that if we add two things in the domain, and apply the adjoint map, that's the same as applying the map and then adding them, or similarly with scale multiplication. And a lot of people had this set up correctly, and then sort of said, some people kept going with it, which is great, and some people said, okay, I know what I need to show, how do I actually show it? And the point here is to make any further progress, we have to use the fact that this is actually a map defined from an inner product, okay? So I'll give you the hint. The hint is that no, it's not linear, okay? So this property is gonna hold, this one's just fine, and this is the one that's not gonna hold, okay? So, there was a good comment from somewhere, I don't remember where, but someone said, well, it works if the field is the reals, and it doesn't work if the field is the complex numbers. So, let's just take a guess. If someone gives you that information, where do you think we're going to see the problem? If I tell you this isn't true, then it's something that goes wrong only in the complex case, who wants to guess the correct statement? Or, say again?
Is it the conjugate of the number?
It's the conjugate. So the point here is that if we take the adjoint of lambda s, what we get is lambda bar times the adjoint. So the conjugate of, okay. So it's not linear. It's still pretty nice function, but it's not a linear function. So we want to be careful. So I'm not going to go through the rest of the proof. I recommend that you try this. If you get stuck, feel free to check in with me, post it on the forum, we can work through it. But it's worth sort of just figuring out how you would set something like this up. And we shouldn't be so surprised that a scalar is gonna come out with a conjugate. And just in a very, very vague way, before we keep going, why is this not surprising? Well, you're moving t star across to the other side. And we know if you want to pull a scalar out from the right side of an inner product, it comes out with a conjugate. So maybe that shouldn't be so surprising that we see that happening. So play around with it a little bit more, try to work this out. Let me just point out that even though it's not a linear map, it is still a pretty nice map. There's some other nice structure we have. So, which on this list is other properties. One of the ones that's really useful is that suppose we have composable maps, okay? So in the context where ST makes sense, so here we have 3 vector spaces and we have composable maps between them, then you could say, well, what happens if we compose the adjoints? And if you look at the possible compositions that would make sense, what you find out is that this is actually equal to T star S star. So that's a nice property. And somehow here, we're saying that even though we don't quite have a linear structure, we're composing functions. So it's nice that we can understand how adjoint interacts with composition. Something else that's useful and nice and easy to prove is that if you take the adjoint of, this one. If you take the adjoint and the adjoint again, this is a sort of, that's not a good sign. Well, I said to someone before class that the day was so nice outside, I wish we could just write with chalk on the side of a building in the sunshine. So that's our backup plan if lights go off again. Try this. So if you take the adjoint twice, what you actually get back is just T itself. And we're going to see that a little bit later on. Okay, so these are just basic properties, but any questions just as we start? And we like adjoints of general linear maps, but we really like understanding the adjoints of operators. Yeah?
Is the adjoint unique?
Oh, that's a great question. Is the adjoint unique? Let's vote. Who thinks the adjoint, so we'll vote yes versus no, and we'll just decide mathematics that way. Who thinks the adjoint's unique? Who thinks it's not? Who's just a skeptic until they've seen it proved for themselves? There we go, got some of those. Okay, yeah, the adjoint is unique, okay? And so the point here is that if you think about how our construction came, the statement of the Riesz representation theorem said there's a unique vector that has that property, so that uniquely defines a map T star. So totally reasonable question. It's sort of, this is sort of what you could call a definition theorem, because it kind of has some results hidden. Even though I'm introducing a new object, I'm also claiming things about it. I phrased it as the adjoint rather than an adjoint, but it's a good question to ask. Other questions? Okay, then what we actually want to do is talk a little bit about adjoints of operators. And let me just motivate this 2 ways. So I said that it's property here that if you happen to be able to compose two linear maps, then you have that the adjoint of the composition is the compositions of the adjoints in the other direction. But of course, if you're working with operators, where you're just going from the vector space to itself, then you can always compose. So it says immediately that you'd have some situation where you might be able to see this relationship. You don't have to worry that you're going to get maps which aren't composable. So that's sort of the first thing you want to do. First reason to think about adjoints of operators. And the second thing is that if you have an adjoint of an operator, then we have that both T and T star are both linear maps in the same space. So we can compare them and we can say what property do they have. So the cartoon that's going to kind of guide us is that we have, this is our space of all operators. And now we want to narrow down what operators we consider based on something about their adjoints. So the nicest possible situation we could have, and this is a small circle because it's not most operators. I mean, what's the nicest possible relationship you could have between two maps in the same space is that they actually agree. So we're going to be interested in the kind of linear maps that have the property that are equal to their own adjoints, okay? And so an operator is called self-adjoint if T equals T star. So definition, T is self-adjoint if T equals T star. And now it's important that we're really only working in the operator world, okay? And most of the time, T is not going to be equal to T star. We can see examples where that's true, but it's not going to be most of the time. So let's notice that there's still a relationship we could have that's not quite as nice as that, but is still more restricted than all operators. And it might not be the first thing you come up with, but it still turns out to be pretty nice that T, T star, and T star T are equal. So if T commutes with its adjoint, then we say that the operator is normal. Okay, and so these are important classes of operators, and what we're going to try to do is build up some techniques for studying them, understand how we can detect some of these properties from matrices, because this is especially useful for trying examples and testing things out, and give a hint at sort of other properties outside of just adjointness that justify these as an interesting class. So even though these are definitions that are given in terms of the adjoint, an operator turns out to be self-adjoint, can give you a different kind of classification. And so what we're going to work into is something, next week our big result is called the spectral theorem. It's sort of the culmination of everything you've learned in linear algebra, and we're almost ready to state it properly. So let's see something about operators of this sort. Let's just do an example first. So I'm going to claim, so let's say let U be a subspace of V, and my claim is that orthogonal projection to U is self-adjoint. Okay. So this is a claim. Let's see if it's true. Okay. So we remember what orthogonal projection to U is. This is what we talked about last time. We have our vector, and we split it into as a sum of a vector in U and a vector in the orthogonal complement of U. So anytime we have a vector on VI, we can write VI as UI plus WI, where UI is in U and WI is in the orthogonal complement of U. Okay? And so I want to know what happens. I want to just check. Here, since I'm telling you it's self-adjoint, instead of working out what the adjoint is, we just want to check that in fact this holds. So let's just see this. So let's say I take the inner product of some V1 and V2, and I want to see what happens if I take this inner product. So that I'm taking the projection of V1 to U, and then taking the inner product of V2. And my claim is that this is equal to V1 PU of V2. Okay? So this is provisional, but let's work out what this side is and work out what that side is, and then we're going to see at the bottom if they're going to agree. Okay? So here, let's start by just rewriting this using orthogonal projection. So this is PU applied to U1 plus W1, inner product of U2 plus W2. And on the other hand, on this side, we have V1 PU of U2 sorry, I want to write that one out fully. Okay, and now this is easy because we're just going to take the projection of this, and so we just throw away the w part. So this says this is just u1 inner product with u2 plus w2, and this we still have our u1 plus w1 in the first place, but in the second part we're throwing out our w2 and we just have our u2. And now we're going to use properties of inner products to say, what's the way we can simplify what this is equal to? We can write it out in sort of 3 steps, or if someone can give me a nice clean statement out loud, we'll write it efficiently and then talk about it. What's the simplest thing I can write for that picture?
Can we split it using distributive law?
Okay, we can split it using distributivity. Now, if you remember, when we set up the axioms for an inner product, we actually said that we can split up sums into sums of inner product only in the first step. So what we could do is we could flip this, take the conjugate, split it into 2 things, take the conjugate of both of them and flip it back. Okay? So what I'm just going to write here is by axioms, where it takes a couple steps. This is u1, u2 plus u1, w2. Okay? So this is not applying a single axiom as written. It's actually applying 3 axioms, but I want you to be comfortable going from here to here. If that's not clear to you while you're doing it, write it out carefully with the axioms. In something like an exam setting, it would be fine to write by the axioms of an inner product this holds, because it's sort of an immediate computation. Okay? But swap, distribute, swap back. Okay? And now we have something even simpler. We can kill one of these, so which one can we kill off? This is 0 because by hypothesis, W1 is in the orthogonal complement of U. Okay? So down here, we just get U1, U2. And over here, we can play the same game. And here, we don't even have to do any swapping. This is just U1, U2 plus W1, U2. Same argument lets us kill this off. And we end up with U1, U2. Okay? So now we say, yes, these 2 things are equal. And since they're equal, we can get rid of our question mark. Okay? So we had, in this case, when you're handed 2 maps, checking that they're adjoints of each other is easy. In this case, I sort of gave you that. So if you want to work out what the adjoint is maybe a little bit more complicated. You have to figure out how to write down the map. But here we can just verify. Okay? Any questions on this example? So we have at least one example of a self-adjoint operator. We have this idea that we've defined the class of things, at least something exists. Notice, and this is sort of implicit in how I do this, that if you're self-adjoint, you're obviously normal. Because if you're self-adjoint, then t equals t star, so you're just writing down t squared equals t squared. Okay? Let's see one example of how normality is more flexible. Okay? So what do I mean by this is, let's say suppose t is normal, then I claim that t minus lambda I is also normal, where here lambda is a scalar. Okay? So why is this helpful? Well, it at least gives us a way to say once we have some normal things, here's how we might generate others. Okay? And again, this is going to be an easy proof, but let's just see it to get used to how normality helps us. So if we want to see that t minus lambda I is normal, then we just have to examine what happens when we take the adjoint of t minus lambda I times t minus lambda I. Okay? And we want to see that we could have done that in the other order. Okay? So here's where we're going to use some of our properties up here. We don't have linearity, but we do know what to do with linear combinations of operators. So we can rewrite this as t star minus lambda bar I star times t minus lambda I. Okay? So I just used a property that I hadn't proved, but it's an important one in the case of operators. The adjoint of the identity is the identity. But if you think about the definition of the adjoint, that should be true, right? Taking the inner product of UW, well, you better get UW, so it's identity. Yes?
Didn't you just prove that?
Didn't I just prove it? Did I?
Well, as a special case of the projection thing?
I proved, so projection onto the whole space is self-adjoint. There we go. Great. Thanks. Okay. Having just proved that, excellent. Corollary, thank you. Okay, thanks. Great. So, okay. So now we keep going. So now let's just expand this out, and then this is just bookkeeping. Okay. So what do we have here? We have our t star t. We have minus lambda bar I star t minus lambda t I, we can get rid of that I, and then we have plus lambda bar times I, okay? And the only interesting thing we have to do here before we can unfactor is because when we're given that t is normal, we can now swap these. So this is t star, this is where we use normality, and then we have our lambda bar. I lost the t, I dropped the t, hold on. I want lambda bar, that's it. Right? Hold on just a second. Keep me honest. This is lambda bar I star t. And then that one, and then this is we can get rid of I star, and just make this t minus lambda star plus lambda bar I. And now if we just factor it in the other direction, we'll get what we want. So this is t, let's factor carefully. Probably the easiest way to do this is rather than unfactoring is if I just write out the other one and come back up. Because then so let's just do it that way for the second. So I want to look at what happens if I take t minus lambda I times t minus lambda I star, and now expand this and do the multiplication the other direction. This is my t star minus lambda I t. Sorry, I'm trying to simplify the kind of routine stuff, but I don't want to make a mistake or underline anything. So this is our t minus lambda I times t star minus lambda bar I star, which is the same as I. And now I'm going up. We have to see that these things are going to meet in the middle. This is my t star. Now I have minus lambda t star, and I have minus lambda bar t. And then I have plus lambda bar I. And now, it works. And now we just check that these all match up. Okay, so we've got these match, and these match, and these match, and these match. So they're pretty equal. Okay, so we just checked that these things can be. Okay. So again, kind of a routine computation using the properties, but it's nice to see that we can extend normal operators we know to new ones. Okay, now, sometimes, depending on how your linear map is given to you, you're going to just work through things with formal properties. Sometimes you're going to use a particular definition of the map. But whenever we're working on operators in the context of finite dimensional vector spaces, it's really efficient to work with matrices. And one of the things that's very practical about adjoints is that if you choose the right basis, then it's very easy to give a relationship between the matrix for linear transformation and the matrix for its adjoint. Okay, so I'm going to put that in here so we can keep it on the same section. And what I'm going to do is I'm going to give you the proof for operators, but what I'm showing, and it's written out I think in slightly the long version in the book, this is actually now something that holds with appropriate choice of bases for arbitrary LBW rather than just for operators. Okay, so here are the hypotheses we need. So we have our T is in L of V, and the very important thing is the following: pick an orthonormal basis for V. Okay, so one of the things you'll explore in the worksheets next week in sections is that this is absolutely essential. Okay, and this shouldn't be so surprising because an adjoint is something that's defined using an inner product. So that the idea that we might have to choose a basis adapted to that inner product to get a nice statement about the matrices, that shouldn't seem so unreasonable. But if you choose an arbitrary basis, the relationship I'm going to describe now just won't hold. Okay? So let me give the statement here. The matrix for T, let's call our basis something. Okay? Basis B. The matrix for T with respect to the basis B. Well, I'm going to give a precise relationship for the matrix for T at T star for B. And what it is I'm going to take the conjugate. So any complex numbers as entries in the matrix get replaced by their conjugates. And the transpose. Okay? So I've made two changes. Let's just label what these are. This is the conjugate. And this is the transpose. Okay? And so remember, the transpose takes entry JK to entry KJ, in terms of swapping rows and columns. Okay? So this is great. This says if you are using an orthonormal basis, then you don't have to do any of this work to figure out what your adjoint is. Just swap your matrix and conjugate all your complex numbers. Okay? So in terms of generating examples, it's really nice to have this tool. If you want to check if something's normal, write down a matrix for it, write down the conjugate transpose, and then just multiply matrices and see if they converge. Yes?
Sorry, it's not a question, but
Go for it.
before you rub off that
Yes.
plot, I haven't been taking a picture, so if you could just swap the boards.
Okay, yes, thank you. Sorry, I should have done it before I did something else. Thanks for keeping me honest on that. Okay, I won't rub. Okay, so let's go ahead and prove this. In this case, we're not trying to work things out from scratch. We're already told what the answer is. So let's just check it. So what do we want to do is I want to try to figure out what does T do to basis vector. I guess I'm using e's because that's sort of the traditional thing. It's for an orthonormal basis, even though I call my basis B. I want to know what T of EK is. And let's remember, in the matrix for T, this is the information that's recorded in column K. Okay? So if I want to know what this is, I want to actually know, let's say, what the J entry is in column K. And so if I need to write this as a linear combination of the same basis vectors. And since it's an orthonormal basis, this is really easy to do. So T of EK, remember, is the inner product of T of EK with E1, that's the coefficient for E1, plus inner product of T of EK with E2, E2, and so on, T of EK, EN. Okay? So this is using what we did last time, which says that if you have an orthonormal basis, there's this formula that just tells you how to write down what the linear combination is. Okay? So from this data, what we know is that entry in row J, column K is, so row J is the inner product with EJ, and column K is T of EK. So that's some number, and that tells us in our matrix for T, that's what we have. Okay? And now we're gonna hope that if we take the conjugate transpose, that we're gonna see the same thing. So this is column K of MT. Let's examine column J of MT star. Okay? So T star of EJ tells us about column J of M of T star, again with this basis. Okay? And we're going to play the same trick. Right? We want to know what this is, so let's just write out what we have in terms of our chosen orthonormal basis. So this is T star of EJ, inner product of E1 1 plus dot 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 plus T star of EJ, inner product of EN. Right? And so let's see if we can identify what the entry in row K of column J is. So the entry in row K, column J, is going to be what? Well, column J is telling us what our first entry was, so it's T star of EJ, and row K is going to be inner product with EK. Okay. So what have we actually gotten ourselves to? What's the claim we want to make about the relationship between those two values, whatever they are? Go for it.
If we take the conjugate of the second one, then we met the definition.
Yeah, we want to verify, so we have these two expressions, and what we want is we want to check that this is the conjugate of this one. And if those two things are conjugates, then what we've shown is exactly what we wanted. We say, switch your rows and columns, and then conjugate all the complex numbers. Okay? So let's just do that. Let's just clean this one up a little bit more. So this is, well, I want to get rid of the t in the first place. So let's do it like this. This is the same as EJ t star star EK. Okay, because just took the transpose to the transpose. Sorry, the adjoint to the adjoint. But we said at the beginning, without proving it, but by claiming it as a property, you can verify that the adjoint to the adjoint is just the original map. Okay, so this becomes EJ of TEK, and now you should start getting optimistic because we have almost what we want. We just have the EJ T of EK, and here we have T of EK EJ, but we know how to swap those because this is equal to the conjugate of T of EK EJ, and that's what we wanted. So instead of boxing this one, we'll box this one, and that's what we wanted to show. Okay? So let me put this up for pictures okay. So what we've seen is that we can give these definitions, but it's a completely fair question to ask why we would want to. So I'm a pure mathematician, I get asked that a lot. Like if someone finds out what I do at a party, they're like, you do topology, why bother? Okay, so there's various answers to give, but I think this is always a fair question to ask. So we've defined these things. I have to justify that these are interesting objects to study. So my justification is going to come in terms of relationships to other objects that we've already invested some time and effort into. So here are some properties of self-adjoint and normal operators. We may have time to prove some of these. We will not have time to prove all of them, but let me state them so that they're here. Okay. So one of the interesting properties is that even on a complex vector space, all of the eigenvalues of self-adjoint operators are real. Okay. So this is a first hint that this property of adjoints is connecting to other structure we're already interested in. Okay? Yeah, let me put them all up and then I'll leave a little space. I hope we'll have time to use. Okay. So, great. It's a way to get real eigenvalues. Here's another one. An operator is normal if and only if, well, it turns out there's a relationship between the norm of the operator and the inverse. So, being normal is the same as saying that for all v, the operator and its adjoint change the length in the same way. Here's another one. So if t is normal, then v is an eigenvector for t, if and only if it's an eigenvector for its adjoint. Okay. So this is saying that the eigenvectors for this function and its adjoint function are actually the same. And if you just wanted to make a guess, what would you guess you can say about the associated eigenvalues? I'm not asking you to justify this, just let's say v is an eigenvector for t with eigenvalue lambda. In the nicest possible world, what's the eigenvalue for the same vector for t star? You might think it'd be the same, but I'm going to go for a world that's even nicer, a world of complex numbers where beautiful things happen to complex numbers. What's even nicer than the same? Conjugate. Yeah, okay. So in the book where they prove it, they show you but the vector is the same, but the eigenvalue gets sent to its conjugate eigenvalue. Okay, so in the real case, it's the same. In the complex case, somehow when we have this this operator, which if you do it twice, gives you back to the identity, we want that to pass through conjugation. It gives us a richer structure. And then let's put up one more, and then we'll see if we can see a proof or two. One more is, okay, if T is normal, eigenvectors for distinct eigenvalues are, well, okay, so let's think about what we know. In the regular case, meaning we have no restrictions on our operator, if you have an operator and you have eigenvectors associated to distinct eigenvalues, we know that they're linearly independent, right? Now we're living in the context of an inner product space. So what's even better than being linearly independent? Orthogonal, there we go, okay? So what it's saying is that these operators are really well adapted to the inner product. You need the inner product to define them, and then you get that back out. So that's really nice. I mean, when we picture our most basic example of a nice vector space, we can picture Euclidean space with the standard basis vectors. And so now what we're saying is that if you have a normal operator on Euclidean space, you're going to get, and you have enough distinct eigenvalues, the eigenbasis you get is not just things that are pointing in sort of independent directions, but really looks like some rotation of that standard coordinate axis. And that's a useful property. Okay, let's prove at least one, please. Okay. So let's do an easy one here. Let's start with the eigenvalues of self-adjoint operators. Okay. So let's suppose that let V be an eigenvector for self-adjoint T. Okay. So I want to compare. Let's see, what do I want to look at? I want to compare what happens if I take the inner product of T, V, and V. I want to say as much as I can about this. Okay. So the first thing I can is I say, well, my operator is self-adjoint. So one of the ways I could rewrite this is as VTV. Okay. That's using my self-adjoint property. And now I'm just going to go off to the left and right and try to simplify this till we get a nice result. So what do I have going this way? Well, we know since V is chosen to be an eigenvector, we know that when we apply T to it, we get some lambda V. So this is lambda VV. And on the other hand, over here, it's the same thing. So this is V lambda V. Okay? And where are we going from here? Well, we could do this in a couple steps with conjugation, or we could just use the fact that we know we can pull a scalar out of the second property. If we pull a scalar out of the second place in the inner product, it comes out with its conjugate. So here, this is lambda VV, but over here, we're going to get lambda bar VV. And just to check that we get some content, what we end up with is the statement that as long as the inner product of V with itself is non-zero, we have that lambda equals lambda bar. Okay? But notice that we get that the inner product of V with itself is non-zero because V is an eigenvector. Okay? So since V is an eigenvector, we have that the inner product of V with itself is not equal to 0, and so this implies that equals lambda bar. Okay. So all of the other propositions have fairly straightforward proofs. They're sort of nicely contained in the text. It's a great idea. My suggestion is write down the first line and see if you get that first line, if you can prove them yourself. In most cases, you just have to sort of use the properties. It might not be obvious how to start, but try at least once to look at the text and then see if you can do it. If you get stuck, you can head back and review. Okay? So we'll start talking about the spectral theorem next week, which is going to talk even more about the kind of eigenvectors and eigenvalues you can get for self-adjoint operators. Yeah.